There is a place in the Indian Ocean where the seafloor simply disappears, not gradually, not in the way a beach slopes gently into deeper water. At the Java Trench, the ground drops away into a darkness so complete, so pressurized, so utterly removed from the world above, that for most of human history we simply drew a line on the map and moved on. What was down there, we assumed, was nothing much. The logic seemed reasonable. No sunlight, crushing pressure, hundreds of times what you feel right now, in this moment, simply breathing. Temperatures hovering just above freezing. No food drifting down in any reliable quantity. The deep ocean, science long believed, was a kind of geological silence, stone and cold and darkness, largely undisturbed. The Java Trench descends more than 7 kilometers. That is deeper than Mount Everest is tall, straight down, in permanent black, under pressure that would destroy an unprotected vessel before it reached the bottom. When scientists finally managed to send cameras into those depths, they were not expecting much. What they found surprised researchers. Movement appeared where stillness had been assumed. Forms emerged that did not rely on light. Patterns repeated in ways that were not immediately understood. Some organisms looked familiar at a distance, and then less so the longer they were observed. Others appeared only briefly and were never seen again. Even the trench itself is not still. It sits at the edge of a collision, one tectonic plate grinding slowly beneath another, reshaping the floor over millions of years. The ground down there shifts, sediment cascades, the landscape changes in ways that are slow by human measure, but constant by geological time. The more instruments we send down, the less predictable it becomes, and that is what makes the Java Trench one of the most quietly extraordinary places on this planet. Not because of its depth, but because it keeps returning findings that nudge the edges of what we thought we understood about pressure, about life, about the hidden architecture of our own world. There is still so much we have not seen. So today, we move slowly into the Java Trench and take a closer look at the unusual discoveries recorded there and the parts of that environment that are still not fully understood. And if this kind of calm, immersive exploration is something you enjoy, a like and a subscription keep them going, and they genuinely help more than you might expect. Now let's descend. Far from coastlines and familiar maps, the boundary that shapes the Java Trench stretches quietly along the ocean floor, tracing a long arc beneath the eastern Indian Ocean. It follows the edge of the Sunda subduction zone, a region where the surface of the planet is not fixed, but slowly folding into itself. From above, the water offers no sign of what lies beneath, only an unbroken expanse that conceals a boundary older than most landscapes on land. Here, two immense tectonic plates meet with a patience that resists human sense of time. The Indo-Australian plate moves steadily northward, while the Eurasian plate holds its position, vast and resistant. Where they converge, the denser oceanic plate begins to slide beneath the lighter continental margin. This motion does not happen in sudden visible shifts, but in a continuous descent measured in centimeters per year. Over millions of years, that small movement becomes a force capable of reshaping entire regions of the Earth. As the descending plate bends downward, it creates a long, narrow depression in the seafloor. This is the trench, not carved by erosion or water flow, but formed by the slow surrender of one plate beneath another. The angle of descent, the weight of the crust, and the friction between layers all contribute to the shape that emerges. Sediments carried from distant rivers and coastlines drift down and gather along the edge, some slipping further into the depths as the plate continues its descent. The trench becomes both a boundary and a record, holding traces of processes that unfold far beyond immediate perception. The Java Trench extends for thousands of kilometers, following the curve of the Indonesian archipelago. Its depth is not uniform. Some sections descend more steeply, while others level slightly before dropping again. These variations reflect differences in the underlying structure, in the age and density of the oceanic crust, and in the subtle shifts of pressure that accumulate over time. Even within stillness, there is variation, a quiet complexity shaped by forces that do not pause. Beneath the surface, the descending plate carries with it water trapped in minerals and sediments. As it sinks deeper into the mantle, increasing pressure and temperature begin to release that water, altering the chemistry of the surrounding rock. This process contributes to volcanic activity along the overlying islands, linking the unseen depths of the trench to the visible chain of volcanoes that rise above sea level. What appears separate, ocean and land, is connected through this continuous cycle of descent and transformation. The trench itself is not a finished structure. It remains in motion, shaped by the ongoing convergence of the plates. Small shifts occur along the boundary, sometimes releasing energy that travels through the surrounding rock. Sediment layers are disturbed, slopes adjust, and the precise contours of the trench evolve in ways that are difficult to measure in real time. Over longer spans, these changes accumulate, deepening certain sections while filling others, maintaining a balance that is never entirely stable. This slow collision has been underway for tens of millions of years, and it continues without interruption. The forces involved do not tire or accelerate. They persist with a steady rhythm, indifferent to the surface world above. The trench, in this sense, is not only a place but an ongoing process, a visible expression of motion that is otherwise hidden deep within the earth. In its depth and formation, the Java Trench reflects a kind of quiet persistence. It exists because the planet beneath the ocean is not still, because its outer shell is divided and constantly rearranging itself. What appears as a single continuous surface is instead a mosaic of moving parts, each interacting with the others in ways that shape the world over immense spans of time. Long before any image returned from those depths, the trench existed only as an absence in measurement, a sudden drop in lines traced across charts that hinted at something far below reach. Early oceanographers followed sound rather than sight, sending pulses downward and waiting for their echoes to rise back through layers of water. The delay between signal and return revealed depth in quiet increments, each reading suggesting that the seafloor was not where it had been assumed, but much farther down, beyond the limits of direct observation. These first encounters were indirect, shaped by instruments that translated distance into numbers rather than form. The deeper the readings extended, the more abstract the trench became, a place defined by absence rather than presence. For a long time, this was enough. The technology required to descend physically into such pressure had not yet taken shape, and so the trench remained an outline, a contour without detail. As engineering advanced, attention turned toward the possibility of reaching those depths with physical devices. Early deep-sea missions relied on reinforced cables and weighted instruments, lowered slowly from research vessels that drifted far above. These tools were designed to withstand increasing pressure as they descended, each meter adding force that pressed inward from all directions. Many early attempts failed quietly, equipment lost to the weight of the ocean before it could return any data. Each loss refined the next design, leading to stronger housings, better seals, and more precise control over descent and retrieval. Eventually, submersibles emerged, crafted as enclosed spheres or capsules capable of carrying instruments into the deep. Some were tethered, guided from above, while others moved independently, navigating through darkness using only limited external light. Their descent was gradual, measured not in sudden motion, but in steady sinking as the surface faded into distance and the surrounding water grew heavier and still, expectations remained modest. The prevailing assumption suggested that little would be found beyond sediment and rock, a landscape shaped primarily by geological forces with minimal biological presence. The absence of sunlight, combined with the extreme pressure and cold, seemed to limit the possibilities for complex life. Instruments were prepared to record temperature, pressure, and chemical composition, with less emphasis placed on capturing images of active ecosystems. When cameras were first included in these descents, they were treated as secondary tools, experimental additions rather than central objectives. Early designs struggled with low light conditions and the difficulty of transmitting images through long cables or storing them within pressure-resistant housings. Illumination systems were limited, casting narrow beams that revealed only small portions of the surrounding environment. The moment when the seafloor first appeared on camera did not arrive with sudden clarity. Instead, it emerged gradually as shapes resolved within the constrained field of view. Fine particles drifted through the light, creating a sense of depth that had not been captured in earlier measurements. The ground itself appeared textured, not smooth as once imagined, but layered and uneven, marked by subtle variations in sediment and structure. Movement was among the first unexpected observations. Within the illuminated area, forms shifted, small at first, then more distinct as the camera adjusted. These were not static features of the landscape, but organisms present in a place long assumed to be nearly empty. Their motion was deliberate, adapted to conditions that differed entirely from those at the surface. Some moved slowly across the seafloor, while others hovered just above it, maintaining position with minimal effort. The realization unfolded quietly through repeated observations. What had been expected as a largely inactive environment revealed itself as something more dynamic, shaped not only by geological processes, but by living systems that persisted under conditions once thought too extreme. Each descent added fragments to this understanding, expanding the sense of what the trench contained. In time, the cameras became central to exploration, their images offering a direct connection to a place that had existed for so long without witness. Through them, the trench shifted from abstraction to presence, its depths no longer defined solely by numbers, but by the forms and movements that unfolded within its silent expanse. At first, the images did not seem remarkable, only a narrow field of illuminated ground suspended within a vast surrounding darkness. The earliest footage offered a limited perspective, shaped by the reach of artificial light and the steady drift of the camera as it adjusted to unfamiliar conditions. Fine grains moved slowly through the water, catching the light in brief flashes, then fading back into the dimness beyond. As the recording stabilized, the surface below revealed itself in subtle detail. It was not the smooth, undisturbed layer that many had imagined, but a terrain marked by gentle ridges and shallow depressions. Sediment lay in uneven patterns, as though shaped by forces that continued to act upon it long after settling. Some areas appeared freshly shifted, their contours sharper, while others carried a softer texture, suggesting gradual accumulation over time. Within this quiet landscape, small forms began to register against the background. At first, they were nearly indistinguishable, their movements so slight that they blended with the drifting particles around them. Only through careful observation did their presence become clear. A faint shift along the surface, a subtle displacement of sediment, revealed that something was moving with intention. These early encounters with life did not arrive as sudden discoveries, but as a slow recognition. A shape would pause, then advance again, tracing a path across the seafloor that lingered briefly before settling back into stillness. Another would rise slightly above the ground, suspended for a moment before returning. Each movement carried a quiet precision, adapted to conditions that allowed little excess motion. The sense of emptiness began to soften as more of these forms appeared. Some were small and close to the sediment, their outlines blending with the textures beneath them. Others occupied the space just above the surface, drifting with controlled adjustments that suggested awareness of their surroundings. The camera's light revealed only a fraction of what existed there, yet even within that narrow beam, the presence of life became undeniable. Surfaces that had once been assumed to be inert showed signs of interaction. Tracks crossed through the sediment in faint lines, intersecting and diverging in patterns that hinted at repeated movement over time. Small disturbances suggested feeding activity, where organisms had passed and altered the arrangement of particles. These markings did not remain long, gradually softened by the slow settling of material from above, yet they offered brief records of activity in a place once thought still. The realization that the trench supported active processes unfolded gradually, shaped by repeated observations rather than a single moment of clarity. Each new descent added variation to the emerging picture. Some recordings captured clusters of movement, where multiple organisms occupied the same area, while others showed long stretches of apparent stillness, punctuated by occasional motion. Together, they formed a pattern that resisted simple interpretation. Even the sediment itself appeared responsive. Fine layers shifted in response to passing forms, rising slightly before settling again. In some areas, small clouds of particles lifted from the surface, drifting upward before dispersing. These movements suggested that the boundary between living and non-living elements was not fixed, but part of a continuous exchange shaped by presence and motion. Over time, the accumulated footage transformed understanding of the trench. What had once been approached as a largely static environment revealed a subtle dynamism expressed through small, persistent actions. Life did not dominate the landscape in visible abundance, yet it was woven into the fabric of the seafloor, present in ways that required patience to perceive. The camera, limited though it was, provided a window into this quiet activity. Within its frame, the trench shifted from a place defined by absence to one marked by ongoing interaction, where even the smallest movement carried significance within the broader stillness. In a place where sunlight never arrives, life does not follow the patterns familiar to the surface world. There is no dawn, no shifting of shadows, no gradual warming to mark the passage of time. Yet within this constant absence, living forms persist, shaped not by light but by conditions that remain steady and unyielding. Early expectations had rested on a simple assumption that energy must come from above, carried downward in diminishing traces until it could no longer support complex systems. Without that steady input, the deep was imagined as a place where biological activity would fade to near nothing. The first sustained observations began to soften that idea, not through dramatic contradiction, but through the quiet presence of organisms that moved, fed, and endured in ways that did not depend on sunlight at all. These creatures exist within a narrow balance, where every function is adjusted to conserve energy and withstand pressure that presses inward from all directions. Their bodies often lack rigid structures, favoring softness and flexibility that allow them to remain intact under immense force. Cellular processes operate at a measured pace, guided by temperatures that remain just above freezing. Growth is slow, movement is deliberate, and survival depends on efficiency rather than speed. Without light, vision loses its usual purpose. Some organisms retain reduced forms of eyes, while others show no trace of them at all. Instead, alternative senses become more prominent. Subtle changes in water movement, Faint chemical gradients and distant vibrations carry information through the surrounding medium. These signals replace the need for sight, allowing organisms to navigate, locate food, and avoid contact without relying on visual cues. Pressure shapes life at every level, from the structure of proteins to the composition of cell membranes. In such depths, molecules must remain stable under conditions that would disrupt their arrangement elsewhere. Specialized compounds help maintain flexibility, preventing the rigidification that would otherwise occur. Enzymes continue to function within these constraints, enabling metabolic processes that support life in an environment that seems, at first glance, incompatible with it. The cold further refines these adaptations. Chemical reactions proceed more slowly, and so organisms adjust by lowering their energy demands. Some rely on intermittent feeding, storing nutrients when they become available, and enduring long intervals between meals. Others engage in symbiotic relationships with microscopic life, drawing energy from processes that do not depend on organic material falling from above. For those who first studied these depths, the presence of such life required a shift in perspective. The absence of sunlight no longer defined a boundary beyond which life could not extend. Instead, it revealed an alternative system, one that operates under different constraints but remains equally capable of sustaining complex interactions. The trench became not a limit, but an example of how adaptable living systems can be when shaped over long spans of time. As more observations accumulated, patterns emerged that linked these organisms to broader biological principles. Life did not require light in the way it had once been assumed. It required energy, stability, and the ability to maintain internal balance within external extremes. In the trench, those conditions were met through pathways that differed from those at the surface, yet achieved similar outcomes in sustaining living systems. The quiet persistence of these creatures reflects a deeper continuity within the natural world. Even in environments removed from familiar conditions, life finds ways to exist, guided by processes that adapt to the constraints of place. What once seemed improbable becomes, through observation, an extension of the same underlying patterns that shape life elsewhere, expressed here in forms that align with the pressure, the cold, and the absence of light. Size behaves differently in the deep, as though the usual limits have been gently adjusted rather than broken. Within the narrow beam of observation, certain forms appeared larger than expected, their proportions familiar at first glance, yet extended beyond what similar creatures display in shallower waters. Among these were amphipods, small crustaceans known across many marine environments, here encountered in dimensions that seemed quietly disproportionate to their relatives above. These oversized amphipods did not dominate the landscape in great numbers, yet their presence carried a distinct weight within the frame. Their bodies curved and segmented in the same recognizable pattern, but scaled upward, with limbs that moved in steady coordination across the sediment. The resemblance to their smaller counterparts created a sense of continuity, while their size suggested that the conditions of the trench had influenced their development over long spans of time. This pattern, often referred to as deep-sea gigantism, is not isolated to a single group. Various organisms found at great depths tend to exhibit increased body size compared to related species in shallower regions. The reasons for this shift are layered and subtle, shaped by a combination of environmental stability, metabolic demands, and the distribution of resources. In the trench, where external conditions remain consistent over long periods, growth can proceed slowly but steadily, without the disruptions that characterize more variable habitats. Temperature plays a quiet role in this process. In colder environments, metabolic rates tend to decrease, allowing organisms to allocate energy differently over time. Rather than rapid growth followed by shorter lifespans, some species extend their development across longer intervals, gradually reaching larger sizes. This slower pace aligns with the overall rhythm of the trench, where change occurs without urgency. Pressure, too, influences biological structure in ways that favor certain forms over others. Larger bodies, when composed of flexible tissues, can distribute external force more evenly, reducing localized stress. This does not mean that size alone provides an advantage, but in combination with other adaptations, it can contribute to stability within an environment defined by constant compression. Scarcity introduces another dimension. Food does not arrive regularly, and when it does, it may be unevenly distributed. In such conditions, a larger body can serve as a form of storage, allowing organisms to retain energy from infrequent feeding opportunities. This capacity does not eliminate the challenges of limited resources, but it offers a buffer that supports survival across longer intervals without intake. At the same time, larger size may reduce vulnerability to certain interactions. Predation patterns differ in the deep, and while risk remains, the balance between predator and prey shifts in ways that can favor increased scale. Movement remains measured, conserving energy, while size contributes to presence within a landscape where encounters are less frequent but still significant. The discovery of these enlarged forms did not arrive as an isolated curiosity, but as part of a broader pattern that gradually came into focus. Amphipods provided one of the clearest examples, their familiar shape making the difference in size more apparent. Through them, the idea of gigantism became less abstract, grounded in observation rather than theory. Over time, these findings contributed to a deeper understanding of how life adapts to extreme environments. The trench does not simply host smaller, diminished versions of surface organisms, nor does it rely solely on entirely unique forms. Instead, it reshapes existing biological patterns, extending some, reducing others, and allowing certain traits to emerge more prominently under specific conditions. Within this quiet enlargement, there is no abrupt transformation, only a gradual unfolding guided by the constraints and possibilities of the environment. The amphipods move across the seafloor with the same steady rhythm, their increased size integrated seamlessly into the surrounding stillness, part of a system where even scale adjusts to meet the demands of depth. In the absence of light, the concept of seeing gradually loses its place. There is no horizon to define distance, no contrast to separate one form from another, no shifting brightness to signal movement. Within such conditions, vision becomes less useful over time, and the structures that support it begin to recede across generations, replaced by systems better suited to a world where light does not arrive. Among the organisms that inhabit these depths, many show little sign of eyes at all. Some retain faint remnants, reduced to simple patches that no longer form images, while others have none, their bodies shaped without any trace of visual organs. This absence is not a limitation in the usual sense, but a refinement, a gradual removal of structures that no longer serve a purpose. Energy, once devoted to maintaining complex visual systems, is redirected toward functions that offer greater advantage. The process unfolds slowly, guided by the steady conditions of the environment. Over time, traits that do not contribute to survival diminish, while those that enhance awareness in other ways become more pronounced. In place of sight, sensitivity to the surrounding medium increases. Subtle changes in water movement carry information across short distances, allowing organisms to detect the presence of others without direct contact. These currents, shaped by even the smallest motions, form patterns that can be interpreted through specialized sensory cells distributed along the body. Chemical signals provide another layer of perception. Molecules released into the water disperse gradually, creating faint trails that persist long enough to be followed. Organisms capable of detecting these gradients can locate food, identify potential mates, or recognize the passage of others through the area. This form of sensing does not rely on direct line of sight, but on the gradual diffusion of information through the surrounding environment. Vibration also plays a role, carried through the dense medium with consistency. Small disturbances travel outward, diminishing slowly as they spread. Organisms attuned to these signals can register movement at a distance, responding to shifts that would be imperceptible in more dynamic environments. This sensitivity allows for a form of awareness that extends beyond immediate proximity without requiring visual confirmation. The absence of eyes also reflects a broader pattern of energy conservation. In an environment where resources are limited, efficiency becomes essential. Structures that consume energy without providing sufficient benefit are gradually reduced. Eyes, particularly those capable of forming detailed images, require significant metabolic investment. Without light, that investment yields little return, and so it is minimized over time. As a result, many organisms adopt forms that appear simplified, yet are finely tuned to their surroundings. Their bodies emphasize functions that align with the available sources of information, prioritizing touch, chemical detection, and sensitivity to movement. These systems operate continuously, without the need for external illumination, providing a steady stream of input that guides behavior. The transition away from vision does not occur abruptly, but as part of a long process of adaptation. Each generation carries slight variations, some favoring reduced visual structures, others enhancing alternative senses. Over extended periods, these changes accumulate, leading to populations where sight is no longer central to survival. In this way, the absence of light shapes not only the environment, but the very nature of perception within it. Life continues to interact, to navigate, and to respond, guided by signals that move through water rather than across illuminated space. What might seem like a loss from a surface perspective becomes, in this context, a reorganization, a quiet shift toward forms of awareness that match the conditions of depth. There are moments in the deep when brightness does not arrive from above, but appears instead as a brief, living signal unfolding within the water itself. It does not spread across the landscape or define distant shapes. It exists in small, contained expressions, flickering into being and fading again, leaving the surrounding darkness unchanged. This light is not a reflection or a remnant. It is produced by the organisms that inhabit these depths, generated through chemical reactions that release energy in the form of a soft glow. Within specialized cells, molecules interact in carefully controlled sequences, producing illumination without heat. The process is efficient, shaped by conditions where energy must be used with precision. Different organisms produce different qualities of light. Some emit a steady glow, faint and continuous, outlining their form against the surrounding water. Others create brief flashes, sudden and contained, appearing for only a moment before disappearing. There are patterns as well, sequences of pulses that repeat with subtle variation, forming rhythms that carry meaning within the local environment. The color of this light tends to fall within a narrow range, most often in shades of blue or green. These wavelengths travel more effectively through water, allowing the signal to extend farther than other colors might. Even so, the reach remains limited, creating pockets of visibility that exist briefly, before dissolving back into obscurity. For many organisms, this ability serves multiple purposes. In some cases, it functions as a form of communication. Signals pass between individuals, marking presence or readiness in ways that do not rely on physical contact. The timing and intensity of these emissions can vary, creating distinctions that are recognized by others of the same kind. In other instances, light becomes a means of concealment. Some organisms produce illumination along their undersides, matching the faint ambient light that filters down from far above, reducing the contrast between their bodies and the space around them. This technique, known as counter-illumination, allows them to blend into their environment when viewed from below, minimizing detection. There are also forms of light used in distraction. Sudden flashes can interrupt the approach of another organism, creating a momentary disturbance that allows for movement away from the source of contact. In some cases, glowing material is released into the water, forming a brief cloud of light that lingers as the organism departs. The presence of bioluminescence introduces a dynamic quality to the deep that would otherwise remain entirely unseen. Movement becomes visible not through external illumination, but through the actions of the organisms themselves. A drifting form may reveal its path through intermittent pulses, while a stationary one might remain hidden until it emits a faint glow. This light does not alter the broader environment. It does not accumulate or persist beyond the moment of its creation. Instead, it exists as a series of brief events, each one localized and temporary. The surrounding darkness remains intact, absorbing the light as soon as it fades. Over time, these patterns form a quiet language, one that operates within the constraints of depth and distance. Signals are simple, yet effective, shaped by the need to convey information without excess. The organisms that produce them are both the source and the audience, participating in an exchange that unfolds continuously, though often beyond the reach of observation. In this way, the deep becomes a place where light is not a constant condition, but a living process. It appears where it is needed, carried by the organisms that generate it, then disappears without trace, leaving behind only the memory of its brief presence within the surrounding stillness. Motion in the trench does not follow the rhythms that are familiar near the surface. It unfolds without urgency, without the constant interplay of currents and light that shape movement elsewhere. Here, even the smallest shift carries a different quality, as though each action has been measured in advance, shaped by conditions that favor restraint over speed. Within recorded observations, movement often begins almost imperceptibly. A form that seemed still resolves into slow progression, its position changing so gradually that only careful attention reveals the shift. This drifting is not passive. It is controlled, guided by subtle adjustments that allow the organism to remain close to the seafloor or hover just above it, conserving energy while maintaining direction. At times, this calm motion is interrupted by brief, sudden bursts. A previously quiet figure accelerates for a moment, covering a short distance with unexpected speed before settling again into stillness. These bursts are precise rather than erratic, suggesting responses to stimuli that are not always visible within the frame. The contrast between extended stillness and sudden motion creates a pattern that feels unfamiliar, shaped by intervals rather than continuity. Interaction with the seafloor adds another layer to this movement. Some organisms maintain close contact with the sediment, using appendages to anchor themselves or to push forward in small increments. Their paths leave faint impressions that linger briefly before softening. Others move just above the surface, their bodies aligned parallel to the ground, rising and lowering slightly as they progress, as if guided by contours that are not immediately apparent. There are moments when movement appears almost suspended, as though time itself has slowed within the frame. An organism may remain in place, making only the smallest adjustments to maintain position, while the surrounding environment shows no obvious change. This stillness is not inactivity, but a form of balance, achieved through continuous, minimal corrections that counteract the subtle forces present in the water. The unfamiliar quality of these movements arises partly from the absence of reference points. Without shifting light or visible currents, there is little to anchor perception. Motion occurs against a background that remains largely unchanged, making even small displacements more noticeable, yet harder to interpret. The usual cues that indicate speed or direction are reduced, leaving movement to be understood through its own internal rhythm. Energy conservation plays a central role in shaping these patterns. Each action carries a cost, and so movement is often limited to what is necessary. Long periods of stillness allow for the preservation of resources, while brief bursts provide the means to respond when required. This balance creates a dynamic that differs from environments where movement is more continuous and abundant. Some organisms exhibit behaviors that suggest interaction with unseen features of the environment. They may follow paths that align with subtle variations in the seafloor, or respond to signals carried through the water that are not directly observable. Their movements trace patterns that are consistent over time, indicating that they are not random, but guided by information that extends beyond the visible frame. As observations accumulated, these patterns began to form a quiet language of motion. The combination of slow drifting, sudden bursts, and extended stillness revealed a system adapted to conditions where efficiency and precision are essential. Movement becomes less about covering distance and more about maintaining position, responding to stimuli, and conserving energy. Within this restrained choreography, the trench expresses a form of activity that is easy to overlook at first glance. Yet, with time, the subtlety becomes more apparent, each shift contributing to a continuous, understated flow that defines how life moves through this environment. Beneath the quiet surface of the trench, the ground itself carries a sense of motion that is not immediately visible, yet never fully at rest. What appears stable within a single moment exists within a larger process that unfolds continuously, shaped by forces acting far below the reach of observation. The boundary between tectonic plates, introduced earlier as a distant and steady convergence, expresses itself here through subtle but persistent change. The descending slab does not move smoothly in a single, uninterrupted glide. Instead, it advances in small increments, sometimes pausing, sometimes slipping forward, guided by friction and pressure that build and release over time. This movement is slow when measured against human experience, yet constant enough to reshape the terrain over longer intervals. Sediment that settles along the trench floor is drawn into this process. Layers accumulate gradually, carried from distant regions and deposited along the boundary. Over time, these layers become unstable, influenced by the shifting ground beneath them. Portions compress, others tilt, and some begin to slide, adjusting to changes that occur below their surface. The result is a landscape that does not remain fixed, but subtly rearranges itself as forces continue to act. In certain areas, the terrain forms gentle slopes that descend toward deeper sections. These slopes may appear stable at first glance, yet they exist in a delicate balance. A slight shift in the underlying structure can alter that balance, causing sections of sediment to move downward in slow cascades. These movements do not always occur as sudden events. Often, they unfold gradually, with fine material slipping and settling in a continuous, almost imperceptible flow. There are also moments when movement becomes more pronounced. Energy that has accumulated along the plate boundary may release, transmitting vibrations through the surrounding rock and sediment. These shifts can disturb the seafloor, altering its contours and redistributing material. While such events are brief, their effects can persist, leaving subtle changes in the arrangement of the terrain. The instability of the ground is not chaotic, but part of a broader system of adjustment. Each movement contributes to a gradual reconfiguration, maintaining the balance between incoming sediment and the forces that draw it downward. Over extended periods, this process shapes the overall structure of the trench, influencing its depth and form. Even within shorter timescales, the effects of this activity can be observed. Small ridges may form and then soften, depressions may deepen or fill, and patterns in the sediment may shift in response to underlying changes. These alterations are often slight, requiring careful comparison to detect, yet they reveal that the seafloor is not a static foundation. The interaction between geological motion and the materials that cover the trench creates a dynamic environment where stability is always relative. What appears settled is, in fact, part of an ongoing transition guided by forces that operate beneath the visible surface. This continuous adjustment influences not only the shape of the terrain, but also the conditions experienced by the organisms that inhabit it. As observations continue, the understanding of the trench deepens, revealing a landscape shaped by motion that rarely announces itself directly. The ground shifts, the layers respond, and the overall structure evolves in a slow, steady progression. Within this process, the seafloor remains active, not through sudden transformation, but through a persistent, quiet movement that defines its nature over time. Across stretches of the trench floor, the surface arranges itself into markings that seem almost deliberate, as if the sediment has been gently guided into order. These patterns do not cover the entire landscape, nor do they remain unchanged for long, yet when they appear, they introduce a sense of structure within an environment otherwise defined by subtle variation. Some of these formations take the shape of fine lines that run parallel for short distances before fading. Others form shallow ridges, raised slightly above the surrounding material, tracing arcs or irregular paths that suggest movement across time. There are also disturbances that appear as clustered impressions, areas where the surface has been shifted and then partially resettled, leaving behind textures that differ from the smoother regions nearby. At first glance, it is not always clear how these patterns form. The trench hosts processes that act continuously on the sediment, shaping it through slow accumulation and redistribution. Particles settle, compress, and adjust in response to underlying motion, creating natural variations in texture and arrangement. In some cases, the lines and ridges may arise from these processes alone, guided by gradients in slope or subtle shifts in the ground beneath. Yet, within many of these patterns, there are indications of biological influence. Tracks cross the surface in paths that curve and intersect, maintaining a consistency that suggests repeated movement by living organisms. These trails often follow a meandering course, shifting direction in ways that align with foraging behavior rather than with uniform geological forces. Their edges are defined enough to stand apart from surrounding sediment, yet soft enough to blend back into the surface over time. Certain markings show a sequence of impressions, spaced at intervals that correspond to the motion of appendages moving across the ground. These sequences create a rhythm within the pattern, a repetition that hints at the passage of an organism advancing step by step. In other cases, the disturbances appear as small excavations, areas where the surface has been disturbed and then left to settle again, possibly reflecting feeding activity or the search for material beneath the top layer. Distinguishing between natural and biological origins is not always straightforward. The same forces that move sediment can produce shapes that resemble tracks, while biological activity can be subtle enough to mimic natural variation. Careful observation over multiple recordings becomes essential, allowing patterns to be compared across time and context. When a marking appears consistently in association with observed movement, its origin becomes more apparent, though rarely with complete certainty. The transient nature of these patterns adds to their complexity. Sediment in the trench does not remain fixed, and so the marks left upon it are gradually softened, filled, or reshaped by ongoing processes. A clear trail may fade within hours or days, replaced by a smoother surface that carries only faint traces of what was once visible. This constant renewal means that each pattern represents a brief moment within a longer cycle, a temporary record that is soon absorbed back into the environment. For those studying the trench, these markings offer a form of indirect evidence, a way of tracing activity that may not always be directly observed. They reveal paths taken, areas explored, and interactions with the surface that might otherwise go unnoticed. At the same time, they resist simple interpretation, existing at the intersection of geological and biological processes. Within these subtle arrangements, the seafloor becomes a canvas of quiet activity, where movement leaves its imprint not through permanence, but through patterns that emerge, persist briefly, and then dissolve, contributing to a continuous, shifting record of life and motion. From far above the trench, a quiet descent is always underway, though it cannot be seen in a single glance. Particles begin their journey near the surface, formed from the remains of microscopic life, fragments of organic material, and fine debris that gradually detach and sink. Over time, these elements gather into a slow, continuous drift, moving downward through the water column in a steady, almost imperceptible fall. This process is often described as marine snow, not for its temperature or texture, but for the way it settles, gently and without urgency. Each particle follows its own path, influenced by subtle currents and variations in density, yet all share the same direction. The descent can take days, or even weeks, a prolonged passage that carries material from the illuminated upper layers to the depths below. As these particles travel, they are altered along the way. Some are consumed by organisms that intercept them mid-descent, reducing their size and redistributing their components. Others break apart, becoming finer and more diffuse, while some continue downward relatively intact. By the time they approach the trench, what remains is a mixture of organic fragments, each carrying a trace of its origin from above. When this material reaches the seafloor, it becomes part of a thin, shifting layer that supports life in ways that are not immediately visible. The accumulation is gradual, yet persistent, providing a source of energy that, while limited, is sufficient to sustain a range of organisms adapted to these conditions. The availability of this material is not constant in density, but its steady presence forms a foundation upon which the trench ecosystem relies. Occasionally, larger forms of organic matter descend more rapidly. The remains of a fish or other marine animal may sink through the water, arriving at the seafloor as a concentrated source of nutrients. These events are infrequent, separated by long intervals, yet when they occur, they introduce a temporary abundance into an otherwise resource-limited environment. Organisms respond to these arrivals with increased activity, gathering around the source and consuming what they can before it is gradually dispersed. The impact of such events extends beyond the immediate moment. As larger material breaks down, it contributes additional particles to the surrounding sediment, enriching the local environment and influencing the distribution of organisms over time. These inputs, though rare, play a role in shaping patterns of activity and presence within the trench. The dependence on material from above creates a connection between distant layers of the ocean. What originates near the surface, shaped by processes involving light and primary production, ultimately supports life far below, where those conditions do not exist. This linkage is not direct or immediate, but mediated through the slow passage of particles and the transformations they undergo along the way. Within the trench, the arrival of this material does not disrupt the overall stillness. Instead, it integrates into the existing rhythm, settling quietly and becoming part of the environment. Organisms adapted to these conditions respond with movements that remain measured, aligning their behavior with the availability of resources that arrive without warning yet follow a consistent pattern over time. This continuous descent forms an unseen exchange, connecting distant regions of the ocean through the movement of matter. The trench, though isolated in depth, remains linked to processes occurring far above, sustained by a flow that is both gentle and enduring. Where material settles, it does not remain untouched for long. The seafloor hosts a quiet assemblage of organisms adapted to locate and process whatever arrives, transforming scattered remnants into energy that can be used again. Their presence is not immediately obvious, yet over time it becomes clear that little is left unused, each fragment entering a cycle of consumption and redistribution. Among these inhabitants are scavengers, organisms that depend on fallen material rather than producing their own energy. They move across the sediment with a steady purpose, guided by signals that reveal the presence of organic matter. Their senses, tuned to detect faint chemical traces, allow them to locate sources of nourishment that may be dispersed or buried beneath thin layers of sediment. Competition in this environment unfolds without urgency, yet it remains constant. Resources are limited and unpredictable, arriving in quantities that rarely meet the needs of all who depend on them. When material becomes available, multiple organisms may converge, each responding to the same subtle cues. Their interactions are not always direct, but their proximity reflects a shared reliance on the same source. Some scavengers specialize in processing fine particles, moving slowly across the surface and ingesting sediment along with the organic material it contains. Within their bodies, usable components are extracted, while the remaining material is released back onto the seafloor, altered in composition. This process contributes to the gradual transformation of sediment, influencing its texture and chemical properties over time. Others are adapted to larger, less frequent inputs. When a more substantial source of organic matter arrives, these organisms gather and feed in ways that differ from their usual patterns. Their movements become more concentrated, their activity sustained over longer periods as they consume what is available. Even so, efficiency remains essential, as the opportunity is temporary and must be used fully before the material is depleted. Feeding strategies vary, shaped by the nature of the available resources. Some organisms extend structures into the sediment, probing for material that lies just beneath the surface. Others remain above, capturing particles that settle within reach. There are those that combine both approaches, adjusting their behavior depending on the conditions they encounter. Each method reflects a balance between energy expenditure and potential gain. As material is consumed, it does not disappear entirely. Instead, it is transformed, passing through different forms as it moves from one organism to another. Nutrients are broken down, redistributed, and eventually returned to the surrounding environment in altered states. This recycling process supports a broader network of life, extending beyond the immediate presence of scavengers. The persistence of these organisms ensures that the trench does not accumulate unused material over time. Even in a setting where inputs are limited, the efficiency of recycling maintains a continuous flow of energy. What arrives from above becomes part of an ongoing exchange, linking individual organisms through shared dependence on the same resources. Within this system, the role of scavengers is both direct and expansive. They process what others cannot, making nutrients available in forms that support additional life. Their activity shapes the composition of the seafloor, influencing conditions that extend beyond their immediate presence. The movements of these organisms, steady and deliberate, reflect the conditions in which they exist. There is no excess, no wasted effort, only a continuous adjustment to what is available. Through their actions, the trench maintains a balance, where even the smallest fragments are drawn into a cycle that sustains life in a place defined by scarcity. Energy in the trench does not arrive only as falling remnants. In certain places, it emerges from within the earth itself, carried upward through subtle chemical gradients that form where water and rock interact over long periods. These sources do not depend on light, yet they provide a foundation upon which life can organize and persist. At the center of this process are microorganisms, especially bacteria, whose activity transforms simple compounds into usable energy. Rather than relying on sunlight to drive their metabolism, they draw from chemicals such as hydrogen, sulfide, methane, or other reduced substances released from the underlying crust. Through a series of reactions, these compounds are combined with oxygen or other elements present in the surrounding water, producing energy that supports cellular function. This process, known as chemosynthesis, parallels the role that photosynthesis plays near the surface, though it unfolds without illumination. The organisms involved do not require light to generate organic material. Instead, they build it directly from inorganic substances, using chemical energy as their source. The result is a system where life begins not with sunlight, but with reactions that occur deep within the earth. Bacteria capable of this form of metabolism often gather in dense communities, forming thin layers or clusters along surfaces where these chemical conditions are most favorable. Their presence may not be immediately visible, yet their activity influences the environment in measurable ways. As they process these compounds, they alter the composition of the surrounding water and sediment, creating localized zones where certain nutrients become more available. These microbial communities serve as the base of a distinct ecological network. Other organisms interact with them in various ways, some consuming the bacteria directly, others forming symbiotic relationships in which both participants benefit. In these partnerships, larger organisms may host bacteria within specialized tissues, providing them with access to the necessary chemicals while receiving energy in return. This arrangement allows complex life to persist in areas where external sources of organic material are limited. The presence of chemosynthetic life introduces a parallel pathway for energy flow within the trench. While material descending from above continues to contribute, These chemical processes provide an additional source that operates independently. Together, they create a system that is not solely reliant on distant surface conditions, but can sustain itself through interactions occurring at depth. The conditions required for chemosynthesis are specific, often associated with areas where geological activity brings chemically rich fluids into contact with seawater. These interactions may occur along fractures in the crust or within sediments where reactions take place gradually. The resulting environments are not widespread, yet where they exist, they support communities that differ from those found elsewhere in the trench. Over time, the recognition of these processes has expanded the understanding of what is necessary for life to exist. Sunlight, once considered essential, becomes one of several possible sources of energy rather than the only one. The ability of organisms to adapt to chemical energy reveals a flexibility that extends beyond earlier assumptions. Within this framework, the trench becomes not just a recipient of material from above, but a site of internal generation. Energy arises from interactions that occur beneath the seafloor, carried upward and transformed by living systems into forms that support a range of organisms. This quiet production continues without interruption, sustained by the steady conditions that define the environment. Bacteria process, organisms interact, and energy flows through pathways that remain largely unseen, yet are fundamental to the persistence of life in these depths. Beneath every visible form in the trench, there exists a layer of life that does not reveal itself to the eye, yet extends across the seafloor in quiet abundance. Within the sediment, between grains that appear still, countless microorganisms occupy spaces so small they pass unnoticed, forming communities that shape the environment from within. These bacteria are not scattered randomly. They organize in thin layers, each responding to subtle differences in chemistry, pressure, and the availability of nutrients. Within a few millimeters of depth, conditions can shift, and with them, the composition of microbial life changes as well. Some thrive closer to the surface of the sediment, where organic material settles, while others exist deeper, drawing energy from compounds released through slow geological processes. Their activity is continuous, though it unfolds at a scale that resists direct observation. As particles settle and become part of the sediment, bacteria begin to process them, breaking down complex organic matter into simpler forms. This transformation does not happen all at once. It proceeds in stages, with different groups of microorganisms contributing at each step, passing intermediate products from one to another in a chain of interactions. In doing so, they alter the chemical environment of the trench floor. Oxygen, when present in small amounts near the surface of the sediment, is gradually consumed. Below this thin layer, other processes take over, involving compounds such as sulfate or methane. Each reaction produces byproducts that influence the surrounding conditions, creating gradients that shape where different organisms can exist. These microbial ecosystems are structured not by visible boundaries, but by these gradients, which shift slowly over time. A slight change in the supply of organic material or in the movement of the underlying crust can alter the balance, leading to adjustments in the composition of the community. The response is gradual, unfolding over extended periods, yet it reflects a sensitivity to conditions that remain largely unseen. Despite their small size, these organisms play a central role in maintaining the flow of energy and nutrients within the trench. By breaking down material that arrives from above or emerges from below, they make it accessible to other forms of life. Without this process, much of the organic matter would remain locked in forms that cannot be easily used, limiting the availability of resources. Their influence extends beyond the immediate environment. The transformations carried out within the sediment contribute to broader cycles that operate across the planet. Elements such as carbon, nitrogen, and sulfur move through these microbial pathways, shifting between different states as they are processed and released. Over time, these changes connect the trench to systems that extend far beyond its boundaries. In this way, the smallest forms of life participate in processes that scale outward, linking local interactions to global patterns. The trench becomes part of a network where even the most remote environments contribute to the overall balance of Earth's systems. The presence of these microorganisms is not marked by movement or visible structure, yet their effects are evident in the composition of the sediment and the conditions that support other life. They form a foundation that is both stable and responsive, adapting to changes while maintaining continuity within the environment. Within this hidden layer, activity continues without pause, guided by processes that operate at the limits of perception. The sediment, though quiet in appearance, contains a complex and active world where microscopic life shapes the conditions that define the trench as a whole. Weight in the trench is not something that rests from above, but something that surrounds completely, pressing inward from every direction at once. It is constant, without fluctuation, increasing steadily with depth until it reaches levels that reshape the behavior of matter itself. Nothing within this environment exists outside its influence. For organisms that live here, structure must respond to this pressure rather than resist it. Rigid forms, common in shallower waters, become less suitable as depth increases. Instead, many bodies are composed of soft, flexible tissues that allow external force to distribute evenly. This reduces the risk of collapse, as there are no hollow spaces or compressible cavities that might fail under stress. The absence of internal air spaces is essential, since any trapped gas would compress rapidly, disrupting balance and function. Movement within such conditions follows this same principle. Muscles and connective tissues operate within a framework that accommodates pressure rather than opposing it. Motion is often smooth and continuous, without abrupt strain on any single point. This design supports stability, allowing organisms to maintain form and function within an environment where force is constant. At the cellular level, adaptation becomes even more intricate. The molecules that make up living systems must remain stable under compression that would alter their shape elsewhere. Proteins, for example, depend on precise folding to function correctly. Under high pressure, these structures can become distorted, yet organisms in the trench produce variations that retain their shape despite these conditions. Their molecular composition is subtly adjusted, ensuring that biochemical processes continue without interruption. Cell membranes, which define the boundaries of living cells, also reflect this adaptation. They must remain flexible enough to function, yet stable enough to resist collapse. In deep environments, these membranes often contain specific lipids that preserve fluidity under pressure. This balance allows substances to move in and out of the cell while maintaining integrity. Enzymatic reactions, which drive metabolism, proceed at a pace influenced by both pressure and temperature. In the trench, these reactions are calibrated to operate efficiently despite the constraints. The chemistry of life continues, not by overcoming the environment, but by aligning with it at a fundamental level. The influence of pressure extends beyond individual organisms, shaping the entire ecosystem. Interactions, movement, and even the distribution of species reflect the conditions imposed by depth. Life persists not in defiance of pressure, but through a continuous adjustment to its presence. For humans, these conditions remain beyond natural tolerance. The human body is adapted to a narrow range of pressure, with internal systems that depend on stable differences between inside and outside. As depth increases, these differences collapse, and without protection, the body cannot maintain its structure. Tissues compress, gases dissolve into the bloodstream, and vital processes are disrupted. Even with advanced technology, reaching such depths requires carefully engineered environments that replicate surface conditions within a sealed space. Submersibles must be constructed to withstand immense external force, protecting the interior from the surrounding pressure. Without such protection, survival is not possible. In contrast, the organisms of the trench do not require isolation from their environment. They exist within it fully, their structures and processes aligned with the conditions that define their world. Pressure, which limits human presence, becomes an integral part of their existence. Within this constant compression, life continues with a quiet consistency. Every form, from the smallest cell to the larger organisms that move across the seafloor, reflects an adaptation that allows it to remain intact and functional. The trench, shaped by depth, becomes a place where pressure is not an obstacle, but a defining element of life itself. Forms in the trench often seem to dissolve at the edges, as if their boundaries are only loosely held together. When light passes through them, it does not reveal a solid outline, but something softer, a body that allows illumination to move within it rather than simply reflect off its surface. These organisms appear less like defined shapes and more like shifting presences, composed of material that blends with the surrounding water. Many of these creatures are soft-bodied, lacking rigid frameworks that would otherwise provide structure. Their tissues are composed largely of water, arranged in ways that maintain cohesion without relying on hard surfaces. This composition allows them to exist within the immense pressure of the trench without resisting it. Instead of opposing the force around them, they yield slightly, distributing it evenly and avoiding points of stress. Transparency becomes a natural extension of this structure. With few dense or opaque components, light passes through these organisms with minimal interruption. In an environment where illumination is rare and localized, this quality reduces their visibility even further. When a faint glow appears nearby, it may reveal only a hint of their presence, a slight distortion rather than a clear form. This near invisibility serves as a form of camouflage, though not in the traditional sense of blending with a patterned background. Instead, it minimizes contrast, allowing the organism to remain indistinct within its surroundings. Without sharp edges or strong coloration, it becomes difficult to distinguish where the organism ends and the water begins. The fragility suggested by these forms can be misleading. While their bodies lack hardness, they are not easily damaged within their native environment. The absence of rigid parts reduces the likelihood of breakage under pressure, and their flexibility allows them to absorb minor disturbances without structural failure. What might seem delicate in a different context becomes stable here, suited to conditions that favor compliance over resistance. Movement within these organisms often reflects their composition. Rather than defined steps or strokes, they glide or pulse, their bodies shifting shape as they move. This motion is smooth and continuous, aligned with the properties of their tissues. It requires little force, conserving energy while allowing for controlled progression through the water. The dominance of these forms in the trench arises from the advantages they offer under such conditions. Rigid structures, while useful in other environments, introduce vulnerabilities here, creating points where pressure can accumulate or where damage can occur. Soft, gel-like bodies avoid these risks, providing a balance between structure and flexibility that supports long-term survival. Their simplicity is not a reduction, but a refinement. By minimizing unnecessary features, these organisms focus their energy on maintaining essential functions. This efficiency aligns with the broader patterns observed in the trench, where conservation and adaptation guide the development of life. Within the limited field of observation, these creatures may appear briefly, their forms revealed only when light intersects with their bodies at the right angle. At other times, they pass unnoticed, present yet indistinguishable from the surrounding medium. Their existence is continuous, though their visibility is not. In this way, the trench hosts a population that is both present and elusive, defined not by strong outlines, but by subtle interactions with light and water. Their forms reflect the conditions in which they live, shaped by pressure, scarcity, and the absence of illumination, resulting in bodies that are as much a part of the environment as they are distinct from it. Sound in the trench does not travel as a sudden interruption, but as a slow unfolding carried through dense water with a steadiness that preserves even the faintest vibration. There is no sharp boundary between silence and noise here. Instead, there exists a continuous field of subtle signals, each one emerging, spreading, and fading without clear edges. At first, recordings from these depths seemed almost empty, the equipment capturing long stretches of low, steady background tones. Yet within that apparent quiet, patterns began to reveal themselves. Soft, distant rumbles appeared at irregular intervals, not loud or abrupt, but deep and extended, as though originating far beneath the seafloor. These sounds are linked to the ongoing movement of tectonic plates, where friction and gradual shifts release energy that travels outward as vibration. Such tectonic sounds do not resemble the sudden jolts associated with surface events. Instead, they unfold gradually, sometimes lasting several seconds or longer, their frequencies low and sustained. The water carries these vibrations efficiently, allowing them to travel significant distances without losing their character. Even when the source is far removed, the signal arrives with a clarity shaped by the medium through which it passes. Alongside these geological tones, there are more delicate sounds that suggest biological activity. Some are faint pulses, brief and rhythmic, occurring in sequences that hint at repeated behavior. Others take the form of soft clicks or taps, spaced irregularly, as though produced by movement or interaction with the surrounding environment. These sounds are often difficult to attribute to specific organisms, yet their presence indicates that life in the trench communicates or interacts in ways that extend beyond visible motion. In certain recordings, a low, continuous hum becomes apparent, not tied to a single source, but emerging from the combined activity of many small processes. It may reflect the movement of water along the sea floor, the interaction of currents with uneven terrain, or the cumulative effect of distant vibrations overlapping within the same space. This background presence creates a subtle texture within the soundscape, a constant layer upon which other signals appear. The distinction between silence and activity becomes less defined in this context. What might be perceived as stillness is, in fact, filled with low-level motion and interaction. The absence of loud or abrupt sounds does not indicate a lack of activity, but rather a different scale and expression of it. Sound here operates within a narrower range, emphasizing continuity over contrast. As instruments improved, the ability to detect these subtle variations increased, revealing a more complex acoustic environment than initially expected. Each recording adds to a growing understanding that the trench is not silent, but characterized by a form of quiet persistence, where vibrations carry information about processes both near and distant. The combination of geological and biological sounds creates a layered auditory landscape. Deep rumbles from the shifting crust provide a foundation, while finer signals from living organisms introduce variation and detail. Together, they form a continuous flow, where each element contributes to an environment that is active, though rarely dramatic. Within this space, sound becomes a means of sensing what cannot be seen. It offers a way to perceive movement, interaction, and change across distances that extend beyond the reach of light. The trench, though visually obscured, reveals aspects of its nature through these vibrations, allowing its ongoing processes to be detected in a form that travels steadily through the surrounding water. In this way, the deep is not defined by silence, but by a subtle and continuous presence of sound, where even the smallest vibration becomes part of a broader, interconnected field. At irregular intervals, the slow convergence beneath the trench releases its stored tension in brief, concentrated events that pass through rock and sediment as waves of motion. These earthquakes originate along the boundary where one plate presses beneath another, a zone that holds strain over long periods before yielding in moments that are short in duration but wide in effect. The movement begins below the seafloor, out of sight, as sections of the boundary shift relative to each other. Friction that once held the plates in place gives way, allowing a sudden adjustment that redistributes the accumulated stress. This release sends vibrations outward in all directions, traveling through the surrounding materials with a speed and clarity shaped by their density and composition. Within the trench, these events are not always experienced as dramatic upheavals. The depth and the nature of the environment soften their immediate expression, yet their presence is unmistakable. Instruments record the passage of seismic waves as fluctuations in pressure and motion, revealing patterns that correspond to distant or nearby shifts. The seafloor itself responds, though often in subtle ways that become evident only through careful observation over time. Sediment resting along the trench floor reacts to these disturbances. Layers that have settled gradually may loosen, their structure altered by the passage of seismic energy. In some areas, this leads to slight rearrangements, where fine material shifts position and then resettles. In others, the effect may be more pronounced, with sections of sediment moving downslope, contributing to the ongoing redistribution of material within the trench. The impact on living organisms is shaped by the scale and proximity of each event. Smaller disturbances may pass with minimal direct effect, integrated into the background of continuous motion that characterizes the environment. Larger shifts, however, can alter local conditions, changing the arrangement of the seafloor and influencing the availability of resources. Organisms adapted to this environment respond not through immediate displacement, but through gradual adjustment to the new conditions that follow. These earthquakes also contribute to the release of fluids and gases from beneath the seafloor. As pressure changes within the crust, pathways may open, allowing chemically rich substances to move upward into the surrounding sediment and water. This process can influence local chemical gradients, creating conditions that support specific forms of life, particularly those that rely on chemical energy sources. Over extended periods, the accumulation of these events shapes the overall structure of the trench. Each shift, though brief, contributes to a larger pattern of change, influencing the depth, slope, and composition of the seafloor. The trench is not carved in a single moment, but refined through countless adjustments, each one adding to its evolving form. The timing of these earthquakes does not follow a simple pattern. They occur when conditions reach a threshold determined by the balance of forces along the plate boundary. This unpredictability adds to the complexity of the environment, where periods of relative stillness are interspersed with moments of movement that alter the landscape. Despite their sudden nature, these events are part of the same continuous process that defines the trench. The slow convergence of plates and the occasional release of tension are interconnected, each dependent on the other. Together, they maintain a system that is always in motion, even when that motion is not immediately visible. Within this context, earthquakes become one expression of a broader dynamic, contributing to the ongoing reshaping of the seafloor. Their effects extend beyond the moment of occurrence, influencing the arrangement of sediment, the distribution of resources, and the conditions that support life, all within a framework that evolves steadily over time. At times, the seafloor does not adjust in small increments, but shifts in a more unified motion, as though a portion of the landscape has loosened and begun to move together. These underwater landslides occur when layers of sediment, built gradually over long periods, lose their stability and begin to descend along the slopes that define the trench. The material that forms these layers arrives slowly, settling from above or accumulating through local processes. Over time, it compacts, yet remains susceptible to disturbance. Beneath it, the ground continues its subtle motion, shaped by deeper forces that alter the balance supporting these deposits. When that balance changes beyond a certain point, the sediment no longer holds in place. Triggers for such movement can vary. A passing seismic wave may shift the arrangement of particles just enough to initiate motion. Changes in pressure within the sediment, caused by trapped fluids, can reduce cohesion, allowing layers to slide more easily. Even the gradual steepening of a slope, shaped by ongoing geological activity, can contribute to conditions where stability is no longer maintained. Once movement begins, it often continues with a steady progression. The sediment flows downslope, carrying with it the structures and patterns that had formed on its surface. This motion is not always rapid, but it is continuous, reshaping the terrain as it advances. Fine particles may disperse into the surrounding water, while larger sections shift as cohesive units, altering the contours of the seafloor. As the material moves, it interacts with the existing landscape. Deposits accumulate in lower areas, filling depressions or forming new layers that differ from those above. The redistribution of sediment changes the structure of the trench floor, creating variations that influence future movement and the conditions experienced by organisms that inhabit these areas. The consequences of these landslides extend beyond the immediate event. The newly arranged sediment presents a different environment, with altered textures and chemical properties. Organisms that rely on specific conditions may adjust their distribution in response, while others find new opportunities within the changed landscape. The process becomes part of the ongoing cycle that shapes the trench over time. These shifts also contribute to the instability of the environment as a whole. The accumulation of sediment is balanced by its eventual movement, preventing the seafloor from reaching a fixed state. Each landslide represents a release of material that has been building, a moment where gradual processes give way to more noticeable change. Despite their scale, these events often leave only subtle traces once they have passed. The seafloor settles again, and over time, new layers begin to form, covering the evidence of previous movement. What remains is a landscape that reflects a history of adjustment though the individual events are not always apparent. The trench, shaped by both slow accumulation and occasional redistribution, maintains a condition of continuous change. Stability exists only in a relative sense, always subject to the forces that act beneath and within the sediment. The ground may appear still within a single observation, yet it carries the potential for movement that unfolds when conditions align. Within this environment, underwater landslides are not anomalies, but part of the broader pattern that defines the trench. They represent a moment where hidden processes become briefly visible, altering the arrangement of the seafloor before returning to the quieter progression that continues without pause. Temperature in the trench settles into a narrow range and remains there, unchanged by the cycles that shape conditions nearer the surface. It rests just above freezing, held steady by the depth of the water above and the absence of direct influence from the atmosphere. There is no warming with the passage of time, no cooling with the shift of seasons, only a continuous, quiet constancy that defines the environment. This stability extends across vast stretches of the trench, creating a uniform background against which all activity unfolds. The water does not fluctuate in response to external conditions, and so the organisms that live within it experience a consistency that differs from almost every other part of the ocean. The absence of variation becomes a defining feature, shaping processes that depend on temperature as a guiding factor. Within this steady, cold, biological activity proceeds at a measured pace. Chemical reactions that support life slow as temperature decreases, influencing how quickly organisms grow, move, and reproduce. Metabolism adjusts to match these conditions, operating efficiently within a range that conserves energy while maintaining essential functions. There is no urgency, no rapid progression, only a gradual unfolding that aligns with the environment. Growth, when it occurs, extends over longer periods. Organisms may take years to reach stages that would develop more quickly in warmer waters. This extended timeline reflects not a limitation, but an adaptation, allowing life to persist within the constraints imposed by temperature. The balance between energy intake and expenditure remains central, guiding processes that unfold with quiet precision. Reproduction follows a similar pattern. Without seasonal cues to signal changes in conditions, timing becomes less tied to external cycles. Instead, it may be influenced by the availability of resources or by internal rhythms that operate independently of surface patterns. This creates a continuity where life proceeds without the interruptions or accelerations that accompany seasonal variation elsewhere. Movement, too, reflects this stillness. Organisms do not engage in frequent or rapid activity as the energy required would exceed what is available. Instead, they maintain positions, shift gradually, or respond only when necessary. The surrounding water, stable in temperature and largely free from strong currents, supports this restrained behavior, allowing motion to remain minimal without consequence. The physical environment mirrors this biological calm. Without significant temperature gradients, the water column remains stratified in a way that limits mixing. Layers persist, maintaining their characteristics over time. This contributes to the overall sense of stillness, where change occurs slowly and predictably, without sudden shifts. Even processes that originate beyond the trench are tempered by this stability. Material that arrives from above does so without altering the underlying temperature, integrating into the environment without disrupting its balance. The trench absorbs these inputs, maintaining its steady state while incorporating new elements into its system. This constancy creates conditions where long-term processes can proceed without interruption. Geological movements continue beneath the seafloor, and biological interactions unfold within the water and sediment, all guided by a temperature that remains unchanged. The environment supports continuity, allowing systems to develop and persist over extended periods. Within this near-freezing stillness, time seems to move differently, not through any change in its passage, but through the pace at which events occur. Life adapts to this rhythm, aligning its processes with conditions that do not vary, creating a world where stability is not temporary, but enduring. Distance in the trench is not measured only in kilometers, but in separation from pathways that connect other parts of the ocean. The depth itself creates a boundary that is rarely crossed, limiting the movement of organisms between this environment and the regions above or beyond. Within this isolation, life follows its own course, shaped by conditions that remain distinct and largely uninterrupted. Species that inhabit these depths often evolve within this confined setting, their populations separated from those in shallower waters or in distant parts of the ocean. The barriers are not visible, yet they are effective. Pressure, temperature, and the structure of the water column all contribute to a form of separation that reduces interaction with outside groups. Over time, this limited exchange allows differences to accumulate. Genetic variation still occurs within these populations, introduced through small changes that arise naturally over generations. Without frequent mixing with other groups, these variations are retained and refined within the local environment. Traits that align with the specific conditions of the trench become more prominent, while others diminish, leading to forms that differ from related species elsewhere. This process unfolds gradually, guided by the steady conditions that define the trench. There are no rapid shifts to redirect evolution, no sudden changes in climate or habitat to introduce new pressures. Instead, adaptation proceeds along a consistent path, responding to factors such as pressure, scarcity, and the absence of light. The result is a collection of organisms whose characteristics reflect a long history within this particular setting. Some of these adaptations are subtle, involving adjustments at the molecular or cellular level that support function under extreme conditions. Others are more visible, expressed in body structure, movement, or behavior. Together, they create a range of forms that are distinct, yet connected through the shared influence of their environment. The limited exchange of genetic material between populations reinforces this divergence. When individuals remain within the same region over many generations, their genetic traits become increasingly specific to that location. The introduction of new genetic material from outside is rare, and so the evolutionary trajectory remains focused, shaped by local conditions rather than by broader interactions. This isolation does not imply uniformity. Within the trench, there are variations in terrain, chemistry, and resource distribution that create microenvironments, each supporting its own community. Even within these smaller areas, populations may diverge further, responding to differences that are slight yet persistent. The result is a layered pattern of evolution where separation occurs at multiple scales. The trench, in this sense, functions as a distinct world, not entirely disconnected from the rest of the ocean, but operating with a degree of independence. Its boundaries are defined by conditions rather than by physical barriers, yet they are sufficient to shape the course of life within them. Over extended periods, this isolation contributes to the emergence of species that are not found elsewhere. Their characteristics reflect a lineage that has developed within the constraints and possibilities of the trench, influenced by factors that differ from those in more accessible environments. These organisms carry within them a record of adaptation that is specific to their surroundings. Within this quiet separation, evolution continues without interruption, guided by processes that operate steadily over time. The trench remains a place where life develops along its own path, shaped by isolation and sustained by the conditions that define its depth. Occasionally, what appears within the frame does not align with any familiar pattern, as though the trench briefly reveals something that resists immediate recognition. These moments are rare, emerging without warning, and often lasting only a short time before the scene returns to its quieter rhythm. Yet their presence lingers, not because they are dramatic, but because they do not fit easily into what has already been understood. Some of these discoveries involve organisms whose forms do not clearly correspond to known groups. Their structure suggests elements of multiple categories, yet does not fully match any of them. Appendages may be arranged in unfamiliar ways, or body proportions may differ from those typically observed in related species. These differences are not always extreme, but they are enough to create uncertainty in classification. In other cases, the organisms themselves may be less unusual than the behaviors they exhibit. Movement patterns appear that do not follow previously observed tendencies, or interactions occur that suggest responses to conditions not yet fully identified. These behaviors are not repeated often, making them difficult to study in detail. When they do appear, they introduce possibilities that extend beyond established expectations. The limitations of observation contribute to this uncertainty. Cameras capture only a portion of the environment, constrained by their position and the reach of their light. When an unfamiliar form enters this limited field, it may be visible only briefly, its full structure or behavior not entirely revealed. Without additional perspectives, interpretation remains incomplete, shaped by fragments rather than by a continuous record. Footage that includes these moments often requires careful reanalysis. Initial observations may overlook details that become apparent only through repeated viewing. Subtle features, such as the arrangement of limbs or the sequence of movement, may suggest different interpretations when examined closely. Even then, conclusions are tentative, reflecting the constraints of the available data. There are instances where multiple interpretations remain possible. An observed form may be considered a variation of a known species, or it may represent something distinct. Without physical samples or extended observation, the distinction remains uncertain. The trench, by its nature, limits the ability to collect and study such material directly, leaving many findings open to interpretation. The rarity of these encounters adds to their complexity. Without frequent repetition, patterns are difficult to establish. A single observation, no matter how clear, does not provide the context needed to determine whether what is seen is typical or exceptional. Over time, additional recordings may offer points of comparison, yet gaps often remain. These discoveries also highlight the extent to which the trench remains only partially understood. Each unexpected observation suggests that there are aspects of this environment that have not yet been fully explored or documented. The absence of clear explanations does not diminish their significance, but instead reflects the limits of current knowledge. Within this setting, uncertainty becomes a natural part of observation. The trench does not present all of its patterns clearly or consistently. Some elements remain elusive, appearing only briefly and resisting easy classification. These moments do not disrupt the overall understanding, but they expand its boundaries, introducing questions that persist without immediate resolution. As exploration continues, such findings accumulate, each adding a small piece to a larger, evolving picture. Some may eventually be understood through further observation or advances in technology. Others may remain ambiguous, their details preserved in recordings that capture a moment without fully explaining it. In this way, the trench reveals itself not only through what is known, but also through what remains uncertain, where even careful observation leaves space for interpretation and quiet reconsideration. Reaching the trench requires machines that carry human intention into a place where direct presence is not possible. These vehicles descend slowly through the water column, guided from above or operating with a degree of independence, their design shaped by the need to endure conditions that would otherwise destroy unprotected structures. Submersibles and remotely operated vehicles, often referred to as ROVs, form the primary means of exploration. Each is built around a core structure capable of withstanding immense external pressure. Materials are selected not only for strength, but for their ability to maintain integrity over repeated descents. Thick walls, carefully sealed joints, and compact internal spaces reduce the risk of deformation, allowing the vehicle to remain functional as it moves deeper. Within these structures, instruments are arranged to capture data and images, translating the environment into forms that can be studied at a distance. Cameras, sensors, and sampling tools extend outward, each component designed to operate reliably despite the surrounding conditions. The arrangement is deliberate, balancing the need for functionality with the constraints imposed by pressure and weight. Maintaining visibility presents a distinct challenge. Without natural light, artificial illumination becomes necessary, yet it must be carefully controlled. Light sources are limited in their reach, creating a narrow field of view that reveals only a portion of the surroundings at any given time. Beyond this illuminated area, the environment remains obscured, leaving much of the trench unseen even during active exploration. The presence of light can also influence what is observed. Organisms may respond to illumination, altering their behavior or moving away from the source. This introduces an element of uncertainty, as the act of observation can change the scene itself. Researchers must account for this effect, interpreting what is recorded with an awareness of how it may differ from undisturbed conditions. Communication between the vehicle and the surface adds another layer of complexity. Signals must travel through long cables or be transmitted acoustically, each method carrying limitations. Delays, interference, and constraints on bandwidth shape how information is received, affecting both control and data collection. In some cases, vehicles operate with pre-programmed instructions, returning later with recorded data rather than transmitting it in real time. Mobility within the trench is also restricted. The terrain, with its slopes and variations, requires careful navigation to avoid contact that could damage equipment. Movement is often slow and deliberate, prioritizing stability over speed. This limits the area that can be explored during a single mission, leaving large portions of the trench unvisited. The duration of these missions is finite. Power supplies, whether through batteries or tethered connections, determine how long a vehicle can remain active. Once these limits are reached, the descent must end, and the vehicle returns to the surface, bringing with it only a fraction of the information that exists below. Each of these factors contributes to the broader limitation of exploration. Despite advances in technology, the trench remains only partially observed, its vast extent and challenging conditions restricting the scope of investigation. What is known comes from selected moments and locations, pieced together to form an understanding that continues to evolve. Within this framework, human technology extends reach without fully overcoming the barriers imposed by depth. The The vehicles that descend carry with them the capacity to observe and record, yet they operate within boundaries that define what can be seen and understood. The trench, in turn, retains much of its complexity, revealed only in parts, while the greater whole remains beyond continuous observation. Maps of the ocean often appear complete, their surfaces filled with contours and coordinates that suggest a thorough understanding. Yet, beneath those representations lies a reality shaped more by absence than by detail. The majority of the deep ocean remains unobserved directly, and within that vastness, trenches occupy a portion that is even less explored. Only a small fraction of the seafloor has been viewed with cameras or visited by instruments that provide detailed records. Much of what is known comes from indirect measurements, where sound or remote sensing outlines general shapes without revealing fine structure. These methods offer a framework, but they do not capture the complexity that becomes visible only through close observation. Within the category of deep ocean environments, trenches stand apart in their inaccessibility. Their depth, combined with the conditions that define them, limits the number of missions that can reach them. Each descent requires specialized equipment, careful planning, and significant resources. As a result, the number of direct explorations remains low compared to other regions of the ocean. The observations that do exist are often concentrated in specific areas, selected based on accessibility or prior interest. Large portions of the trench have never been visited by a camera, leaving gaps that extend across distances measured in hundreds or thousands of kilometers. Even within areas that have been explored, coverage is limited, with individual missions capturing only a small section of the surrounding environment. This uneven distribution of data shapes the current understanding. Patterns are inferred from what has been observed, yet the absence of information in other areas introduces uncertainty. Conditions that appear consistent in one location may differ elsewhere, but without direct observation, these variations remain unconfirmed. The challenges of exploration contribute to this gap. Depth imposes constraints on equipment, while the lack of light and the stability of the environment limit the speed at which surveys can be conducted. Each mission must balance the desire to cover more ground with the need to maintain precision and reliability. This balance often favors detailed study of smaller areas over broad coverage. As a result, the trench is known through a collection of fragments, each providing insight into a particular moment and place. These fragments, when combined, form a partial picture, one that continues to expand as new missions add to the existing record. Yet, the overall scale of the environment ensures that much remains outside this picture. The unknown is not simply a lack of information, but a space where possibilities remain open. Observations from one area suggest patterns that may extend elsewhere, but without confirmation, these remain tentative. The trench holds variations that have not yet been recorded, processes that have not yet been observed, and forms of life that have not yet been documented. This incompleteness is not static. Each new descent reduces the unknown slightly, adding detail to areas that were previously unobserved. At the same time, it often reveals additional complexity, suggesting that what has been seen is only part of a larger system. The scale of the ocean, combined with the difficulty of reaching its deepest regions, ensures that exploration proceeds gradually. The trench, though part of the same planet that is otherwise well mapped and studied, remains largely beyond continuous observation. Within this context, knowledge grows through accumulation, each observation contributing to a broader understanding while leaving space for what has yet to be seen. The trench continues to exist as both a studied environment and an expansive unknown, defined as much by what is not yet observed as by what has been recorded. For a long time, the deep was approached as a place defined by limitation, where conditions seemed to restrict life to the simplest possible forms. The absence of familiar energy sources, combined with pressure and cold, led to a view that complexity would diminish with depth, giving way to environments shaped primarily by geological forces. This perspective guided early expectations, framing the trench as a quiet extension of the ocean floor rather than as a distinct system. As observations accumulated, that expectation began to shift, not through a single discovery, but through a gradual accumulation of details that did not align with earlier assumptions. What had been imagined as sparse revealed itself to contain patterns of interaction, subtle yet persistent. Movement, structure, and variation appeared where uniformity had been anticipated, suggesting that the processes supporting life extended further than previously thought. The presence of organisms adapted to conditions without light introduced a different understanding of how energy flows through the environment. Rather than depending solely on external inputs, life in the trench drew from multiple sources, each contributing in ways that supported a network of interactions. This network did not mirror surface ecosystems directly, but it displayed its own form of organization, shaped by the constraints and possibilities of depth. Complexity emerged not through abundance, but through the efficiency and specialization of the organisms involved. Each form occupied a role that aligned with available resources, contributing to a system where even limited inputs were used fully. The relationships between these organisms, though less visible, created a structure that supported continuity over time. This evolving understanding extended to the physical environment as well. The seafloor, once thought to be largely static, revealed a dynamic nature, influenced by processes that operate beneath and within it. The interaction between geological activity and biological presence became more apparent, highlighting connections that were not initially considered. Research continues to refine this perspective, building on the foundation established by earlier observations. New technologies allow for more detailed recordings, capturing aspects of the environment that were previously beyond reach. Each mission contributes additional information, expanding the scope of what is known while also introducing new areas of uncertainty. The contrast between early assumptions and current understanding reflects the progression of knowledge shaped by the gradual accumulation of evidence. The trench, once approached as a place of limitation, now appears as a system where life persists through adaptation and interaction, supported by processes that extend beyond initial expectations. This shift does not imply that all questions have been resolved. Instead, it highlights the depth of what remains to be explored. Each discovery reveals further layers of complexity, suggesting that the current understanding is part of an ongoing process rather than a final conclusion. Within this framework, the trench becomes a space where expectations are continuously adjusted, guided by observation rather than assumption. The transition from viewing it as largely inactive to recognizing its complexity reflects a broader pattern in the study of the natural world, where initial ideas are refined through experience. As research continues, the distinction between what was expected and what is observed becomes less pronounced, replaced by a more nuanced understanding that accommodates both the limitations and the possibilities of the environment. The trench, in this sense, remains an evolving subject, its reality shaped by the interplay between observation, interpretation, and the gradual expansion of knowledge. Far below the surface, the trench continues its slow work, shaping the planet in ways that remain largely hidden yet deeply influential. Its presence is not isolated from the rest of Earth, but woven into systems that extend across continents and oceans. The processes that unfold here connect to broader patterns, linking the depths to the surface through cycles that operate over immense spans of time. Geologically, the trench marks a boundary where the outer layer of the planet is renewed and reshaped. The descent of one plate beneath another is part of a larger system that redistributes material from the surface into the interior. This movement influences the formation of mountains, the activity of volcanoes, and the long-term evolution of landscapes far from the trench itself. What occurs in these depths contributes to the shifting arrangement of the continents, guiding changes that become visible only over millions of years. The material carried downward does not remain unchanged. As it moves into regions of increasing pressure and temperature, it undergoes transformations that release elements back toward the surface in different forms. These processes connect the trench to cycles that influence the composition of the atmosphere and the chemistry of the oceans. The exchange is gradual yet continuous, linking the hidden depths to the broader systems that sustain life across the planet. Biologically, the trench offers insight into how life adapts to conditions that differ profoundly from those found elsewhere. Organisms here operate within constraints that challenge assumptions about what is required for survival. Their existence demonstrates that life can persist through pathways that do not rely on familiar sources of energy, expanding the understanding of biological possibility. The study of these organisms contributes to a wider perspective on evolution and adaptation. By observing how life responds to pressure, scarcity, and isolation, researchers gain a deeper sense of the flexibility inherent in living systems. These insights extend beyond the trench, informing the study of environments that share similar constraints, whether within Earth or beyond it. Understanding extreme environments, such as the trench, also provides a framework for interpreting conditions elsewhere. The adaptations observed here offer models for how life might exist in settings that lack sunlight or experience high pressure, suggesting that the boundaries of habitability are broader than once assumed. This perspective influences fields that explore not only Earth, but also other planetary bodies where similar conditions may exist. The relevance of the trench to Earth science lies in its role as both a site of active processes and a record of past activity. Layers of sediment, patterns of movement, and the distribution of organisms all carry information about how the environment has changed over time. By studying these elements, scientists can reconstruct aspects of Earth's history, tracing the interactions between geological and biological systems. The trench also serves as a reminder of the interconnected nature of the planet. What occurs in one region influences others, even when the connection is not immediately visible. The movement of plates, the cycling of elements, and the adaptation of life all contribute to a network of processes that define Earth as a dynamic system. Within this context, the Java Trench remains significant not only for its depth, but for the insights it provides into how the planet functions. Its continued study adds to an understanding that is both detailed and expansive, revealing connections that extend far beyond the boundaries of the trench itself. Exploration often turns outward, toward distant planets and empty space, yet an equally vast unknown lies within reach, hidden beneath the ocean's surface. The deep sea, and the trench within it, presents a frontier that is closer than space in distance, yet comparable in difficulty, shaped by conditions that limit direct access and continuous presence. The challenges of reaching these depths differ from those encountered beyond the atmosphere, but they are no less significant. Pressure replaces vacuum as the primary constraint, demanding structures that can endure forces pressing inward rather than outward. Movement is slowed by the density of water, and communication becomes dependent on methods that carry signals through a medium that alters and delays them. Each descent requires preparation that parallels the care taken in launching missions beyond Earth. Accessibility remains one of the defining factors. While space missions involve travel across vast distances, the trench requires passage through a vertical column that imposes increasing demands at every stage. The environment cannot be approached casually or explored without specialized equipment. This limits the frequency of missions and the duration of each exploration, leaving much of the region beyond continuous observation. Despite these constraints, the importance of continued research remains clear. The trench offers insights into processes that shape the planet, from geological movement to the cycling of elements. It provides a setting where life operates under conditions that differ from those at the surface, expanding the understanding of biological adaptation and resilience. Each observation contributes to a broader perspective on how Earth functions as a system. The comparison to space extends beyond difficulty. Both environments require technology that extends human presence into places where direct survival is not possible. Both reveal conditions that challenge expectations, offering new perspectives on familiar principles. Yet, the deep ocean holds a unique position, as it is part of the same continuous system that supports life on the surface, connected through processes that operate across different scales. Future missions will continue to build on the foundation established by earlier explorations. Advances in materials, energy storage, and communication may allow for longer and more detailed observations. Autonomous systems may explore areas that are currently beyond reach, navigating the terrain with greater independence. These developments will expand the scope of what can be studied, gradually reducing the gaps in knowledge. At the same time, each new capability introduces further complexity. As more of the trench is observed, additional questions arise, reflecting the depth of what remains to be understood. Exploration does not conclude with the collection of data, but continues as interpretation evolves, integrating new information into existing frameworks. The trench, as part of this broader frontier, represents a space where discovery remains ongoing. It is not defined solely by what has been found, but by what has yet to be observed. The effort to explore it reflects a continued engagement with the unknown, guided by the tools and methods that extend human perception into environments that would otherwise remain beyond reach. Within this context, the deep ocean stands alongside space as a domain that invites careful exploration. Both require patience, precision, and the willingness to engage with conditions that differ from those of everyday experience. The trench, though hidden beneath water rather than beyond the atmosphere, remains a frontier where understanding continues to develop, shaped by each descent and each new observation. Far below the reach of weather, seasons, and surface rhythms, the trench continues in a manner that does not depend on what happens above. Its processes unfold at their own pace, guided by conditions that remain largely unchanged over time. The absence of direct influence creates a kind of separation where the environment develops according to patterns that persist without interruption. Life within this setting operates independently of human presence. The organisms that inhabit these depths do not rely on observation, disturbance, or intervention. Their existence is shaped by factors that have remained consistent across long periods, allowing cycles to continue without the variability introduced by surface activity. This independence is not absolute, as connections to the wider ocean remain, but it is sufficient to maintain a distinct rhythm. The cycles that define the trench move slowly, often beyond the scale of immediate perception. Growth, reproduction, and interaction occur over extended periods, influenced by limited resources and stable conditions. Changes are gradual, accumulating over time rather than appearing suddenly. This steady progression creates an environment where continuity is maintained through subtle shifts rather than abrupt transitions. Energy flows through these systems in measured ways, distributed among organisms that are adapted to use it efficiently. Each element contributes to a broader balance, where inputs and outputs remain closely aligned. The result is a form of stability that supports ongoing activity without requiring large or frequent changes. The isolation of the trench reinforces this continuity. While material and organisms may occasionally arrive from above, these events do not alter the underlying structure of the environment. Instead, they are absorbed into existing patterns, becoming part of cycles that continue as before. The system adjusts, but it does not depend on these inputs to sustain itself. From a human perspective, this independence offers a different way of considering the planet. Much of what is familiar occurs within environments shaped by variability and interaction, where conditions change and systems respond. The trench presents an alternative, where stability and isolation allow processes to unfold with minimal external influence. This does not imply that the trench is static. Movement, transformation, and interaction are present, but they occur within a framework that remains consistent. The absence of rapid change allows these processes to proceed without disruption, creating a sense of continuity that extends across time. The existence of such environments contributes to a broader understanding of Earth as a system composed of many interconnected yet distinct parts. Each operates according to its own conditions, contributing to the overall balance while maintaining its individual characteristics. The trench, though remote, is part of this larger structure, influencing and being influenced in ways that are not always immediately visible. Within this context, life continues regardless of observation. The presence or absence of human attention does not alter the fundamental processes that sustain these ecosystems. They persist, guided by the same forces that have shaped them over time, existing as part of the planet's ongoing activity. This perspective shifts the focus from exploration to continuity. The trench is not defined by whether it is seen, but by the processes that occur within it. Its cycles continue, its organisms adapt, and its environment evolves, all within a framework that remains largely independent of external influence. In this quiet persistence, the trench reflects a dimension of Earth that operates beyond immediate awareness, where life and process continue without interruption, forming part of a system that extends far beyond what is directly observed. There are places on Earth that reveal themselves quickly, offering clear outlines and familiar patterns, and then there are places like this, where understanding arrives slowly, shaped by fragments gathered over time. The trench remains one of those quiet spaces defined not by a single discovery, but by the accumulation of many small observations that together suggest a depth of complexity still unfolding. What has been seen does not settle into a complete picture. Instead, it forms a shifting outline where each detail adds to an understanding that remains open. The organisms, the movements, the structures of the seafloor, and the processes that guide them all exist within a system that resists simple definition. It is not chaotic, yet it does not present itself in ways that are immediately familiar. Its order is present, though often subtle, revealed gradually through careful attention. Time moves differently here, not in a way that can be measured by daily change, but through steady progression. Geological shifts occur over spans that extend far beyond a single lifetime, while biological processes unfold with a patience shaped by the environment. This difference in scale creates a perspective where continuity becomes more visible than change, where what endures carries as much significance as what evolves. The trench exists as part of a larger whole, yet it maintains a character that feels separate, shaped by conditions that remain consistent across long periods. Within this setting, life persists, adapts, and interacts in ways that continue without interruption, independent of whether it is observed. Its presence does not depend on recognition, and its processes continue regardless of attention. There is a quiet balance in this, a sense that much of the planet operates beyond immediate awareness. What is known represents only a portion of what exists, and each effort to explore reveals both detail and limitation at the same time. The deeper the observation, the more apparent the boundaries of understanding become, not as obstacles, but as spaces where further discovery remains possible. This ongoing exploration reflects a broader relationship with the natural world, where curiosity leads inward as much as outward. The trench, though distant from everyday experience, remains connected to the same systems that shape the surface, offering a perspective that expands rather than replaces what is already known. In this way, it becomes less a destination and more a continuing passage, where each observation adds to a narrative that is still being written. The details that emerge are not isolated, but part of a sequence that extends both backward and forward, linking past conditions to those that will follow. For those who find themselves drawn to these quiet explorations, there is always more to consider, more to observe, and more to reflect upon. The trench does not present a final conclusion, but an invitation to remain engaged with what lies beneath the surface, where understanding grows gradually through attention and time. If this kind of calm journey into the less visible parts of our world resonates with you, you can continue following along as more of these places are explored and shared. A simple gesture of support helps sustain these explorations and allows them to continue unfolding, one observation at a time, within a world that remains far deeper and more intricate than it first appears.